quite happy to say that even in this IGF, there is IPv6 network running, so you can connect to internet using IPv6 as well. So if you see your address, you should see an address something along these lines. Right? So we have IP version 4 and IP version 6. Now, again, going back to the point that which I mentioned earlier, we need to have these addresses so that every host or every device that connects to the internet can be uniquely identified with this number, just like a house address. Right? So now we have our network, the one that we talked earlier. It's all connected. Right? So every of these devices, then we have to have an IP address. It could be an IPv4 address or it could be an IPv6 address. So every of these devices will have an address. I mean, nowadays there are, of course, challenges where if you have an IPv4 address and if you have an IPv6 address, how we can talk each other. These are some of the challenges, of course, people are working nowadays. But there are, of course, solutions for those as well. Right? So the bottom line is that every of these devices that we connect has to have this address called an IP address. So what is this IP address is? What are those? They are internet infrastructure addresses. Right? So every of these devices which connects to the internet has got this IP address, whether it's IPv4 or IPv6. And it is a public resource. Right? It doesn't belong to anyone. It is a public resource. And they are being distributed actually by what we call internet registries or regional internet registries. And also, they're not depend on the DNS system. Later on, I'll talk about the DNS system. They're not depend on that. DNS is the domain name system. And also, just to actually emphasize here we are talking about IP addresses. It doesn't mean the intellectual property, the usual IP term that a lot of legal professionals they use, right? So here we are talking about internet protocol addresses, IP addresses. Now this is just to give you a very quick overview of current status of these IP addresses, IP version 4 addresses. We've been distributing these IP version 4 addresses for quite a long time, as I said, about 30-35 years or so. There are some of the historical address space which was distributed before 1990s. And then since early 1990s, since the regional internet registries were formed, they have been distributing these IP addresses. That's the blue area. So when regional internet registries has been distributing this IP address space, there are a number of policies involved because, there are a lot of priorities, things like we need to handle these IP addresses quite responsibly. Things like, we should not waste those. We have to give efficiently to networks. There are so many things behind those. That's why actually the regional internet registries, they distribute this address space and they work together with the internet community in developing these internet policies as well. Okay? And some of these IP addresses are reserved for private IP address space. Things like, probably even in your house, if you connect your laptop computer or if you connect your mobile phone to your router in your house, you might probably use these private IP address space, which is reserved by your service providers or by your administrator. Now, this is just to give you a picture about IP version 6 address space, which I mentioned you earlier. It is a very, very big address space, as I showed you earlier. The yellow area is the address space that we distribute at the moment, right? So to the whole world. So it's a small, very small percentage comparing to the whole IPv6 address space that is being distributed to the community or to the internet users. Now, IPv6 address space is the understanding here is that all the expectation of IPv6 address space is to last for quite long time to the future, right? So that's why we have quite a lot of IPv6 address space available. Now, if you kind of get a overview of internet, Now, there are lots of devices in the internet, they connect through IPv4 networks. And then there are lots of devices they connect through IPv6 networks. So if you want to kind of have a comparison between IPv4 internet and the IPv6 internet, this is kind of a map or network map you can see. So obviously IPv4 internet is quite dense comparing to IPv6 internet, because IPv6 internet is still growing. It is in the very early stages at the moment, so that's why you don't see that many networks or that many devices they connect using IPv6. But it is growing. It is growing in a sort of, very rapid rate. Now let's get into, so that's all about numbers. So initially I mentioned you about the networks, the devices, the protocols involved, how they talk each other, right? So simply TCP/IP is a protocol that we use to connect these devices between each other. It's just like talking each other, language, right? I might be speaking my own language in my country. You might be speaking your own language in your country. If we want to talk each other, if we want to understand each other, we need to agree upon a common language. So in the same way, this is the same thing. So TCP/IP is a common language that when these devices they speak, they understand, they comply on that. Right? So now we get into internet routing. So let's see what is internet routing. So we discussed so far that internet is a collection of networks, right? So collection of networks, and then or collection of devices, they interconnect, and then that becomes networks, and then we connect all these networks. So it's a mesh of these networks. Now we need to actually then go from one of these networks to the other network. If we want to send some information, packets from one place to another place, we have to send all the way from one place to another place, right? So how can we send this? Now we have this system called routing system. Right? Now, if I go back to my previous example, the postal system, the letters, routing system is very similar to the postal system. Right? If you want to send a letter to your friend, we said, okay, you write your address, put the letter into your post box or the mailbox, and then the postman will come and take it to a post office and do some sorting there, and then probably take to another post office, a bigger one possibly, and then maybe send it to another post office in another country, and so on, until you get the letter to your friend's house. So in the same way, in the data communication aspects, when we want to send these packets from one place to another place, we have to rely on this routing system, which is very similar to the postal system. So we have things called routers. Now routers are just like post offices. Now in the post offices, what we do is, we do sorting. The post office, the postmen, they collect all the letters, and then they probably put into different baskets, maybe one going into one country, another basket, all the letters going into another country, and so on. In the same way, the routers, they do sorting. They check all these packets, the headers, if you remember. They check the headers, and then it finds the destination, where these packets are destined to, which networks, right? And how does it match, or how does it find it? We have something called a routing table. So routing table is very, very important, especially if you want to send your if the router wants to take this decision and send those packets from one router to another router, or one network to another network. So routing table is one of the important concepts in internet routing. So we have this thing called routing table. Now what is there in the routing table? Now in the routing table, we have these address blocks, IP address blocks. So if this is just a very, very high-level example of a routing table. If you see in this routing table, you have those IP address blocks, IPv4 blocks. So in the real life, if you go to a house, if you go to a new house, if you buy a new house, And if you want your family and friends to visit you, you have to tell your house address to your friends and family. If you don't tell, they cannot visit you, right? So you have to actually announce, or you have to tell your house address to the others. So in the same way, even in the data communication, if some organization gets an IP address block so that they can give those IP addresses to their devices, when they get IP address block to their network, they have to tell the world that they have received this IP block, right? So that others can send the traffic to that network. That's how it works, just like in the real life way. So usually, if you are an organization who gets an IP block from your ISP, right? Either your IP address block can be announced to the global routing table by yourself or through your ISP or internet service provider. But the bottom line, of course, is we have this thing called global routing table, which announces all these prefixes, what we call the IP address blocks, which are being announced to the internet. So that's the list of prefixes, list of IP address blocks. Now this routing table can grow over the time. When more and more networks get connected to this internet, the routing table grows, right? So that's the idea of a routing table. So let's see how this routing table goes. Now we have the internet and we have a global routing table over there. Now if you see, this is my, let's say my organizational network. I have got the IP address block, that one, 202.12 dot something. And that has been, if we can announce that to the routing table, right, if we can announce this to the internet and announce to the routing table so that the traffic can then pass from internet to our network. So if I'm going to run a web server, and web server is running one of these IP addresses in my network, and if someone wants out there to visit my web server, they can reach my network in this way. But to do that, I have to announce my network to the global routing table. Okay? So this is how the routing works. Now this works internally as well within our local network. It is just like, even go back to your postal system. If you want to send a letter to a certain country, right? Now I am in Indonesia. If I want to send a letter to another country, the post office in Indonesia doesn't really care about the street address of the other country. Their interest is sending the letter to that country. And within that country, the postal system in that country will take care of that and deliver it to the appropriate house. In the same way, we have global routing and local routing. So that if I want to do some routing inside my network, I can still do it locally. Right? So this is what we call the local routing. We do the local routing here. So even for that, I have to maintain a similar routing table, but that is locally. That doesn't need to really go out to the internet and announce to the global routing table. Okay. So this is how the traffic passes to my computer all the way from one network to another network, from one device to another device. The traffic passes all the way and get to my device. Now, if you see some statistics, how the internet has been growing over the last many years. Now, this is the growth of the IPv4 routing table. So any device that connects, or any network that connects to through IPv4, that many prefixes, that many networks have been announced to the global routing table. So as of a few days ago, as of 16th of October, we have got around 481,000 something prefixes or networks announced to the global routing table, right? So almost 500,000 networks, IPv4 networks around the world has been announced to the internet to the global routing network so that we can send traffic to all these networks. So you can see that how the internet has been growing over the last 20, 25 years, right? So very early days, routing table was not a big problem, right? And remember, when this routing table grow, what implications will it have? When the routing table grows, the routers need to take decisions, right? It is a table. So routers need to go through this table and find a decision or take a decision to which network they have to forward this traffic. So when the routing table grows, definitely the router performance goes down. And router is a very important component of this whole data communication system, right? So that's why the routers are very important. And as I mentioned it is just like those post offices in our postal systems, so that they can take the decisions and then forward to appropriate routers. So the internet routing table has been growing over the last number of years. You can see that it has been growing in a sort of an even exponential rate. So this is actually a challenge, right? This is a challenge because the routers should be able to handle this. Otherwise, if the routers take time, if the router take time to take a decision, the internet performance can go down. It will be quite slow, right? So as a whole, especially if you are operator, if you are ISP, even if you're an organization who try to address or try to announce your address space to the internet, this is something that organizations needs to think about to make sure that routing table should be kept at a manageable level, right? So this is the same figures, but in IPv6. Earlier the numbers were on IPv4, but this one is on IPv6. You can see the numbers in IPv6 is almost around 15,000, 16,000, comparing to 500,000 in IPv4. So it's not much comparing to IPv4, but as I showed you earlier, still this is growing. IPv6 internet is still growing. There are every day, day by day, more and more organizations, more and more networks, they are announcing IPv6 networks to the internet, right? That's why you can see it is growing over the time. All right, so now how they are all connected. So these are what we call routed backbones, right? So the operators, ISPs, when they get these IP address spaces, when they plan their networks, when they design their networks, they can design their networks to cover regions or countries or even global, right? So when you talk about these networks, it can grow from a very small network to a very large network covering even the whole world, right? So there's no really, here we are not talking about any specific boundary here because they're all networks, right? And then, so they're all physical circuits running all around their networks so that they can send these information, this data, these packets from one place to another place, right? Now also we have some infrastructures called internet exchange points. Now what are these? Now these are, we talked about different internet operators, service providers. Let's say I am a service provider, right? I am a service provider and I have my customers, right? Think about your ISP. You are a customer, your house, you have an internet connection, you connect to an ISP. In the same way, there's another ISP and they also have their customers and so on. But if my customer wants to talk to the other ISP's customer, the traffic sometimes can pass through various, very long paths. Because if I connect to some other ISP's providers somewhere else in another country and so on, and if other ISP also connect to the same way, the traffic can flow from quite far away, right? So the response times are not very good. Sometimes you might be in one country, but really your traffic might go into so many other, other side of the world and still come back again to your own country because how these infrastructures are designed, Right? So this is why we have this thing called Internet Exchange Points, where we can optimize the routability in terms of local traffic. So for example, if one customer wants to talk to another customer, if these ISPs, if these operators, if they can connect to one common point, or what we call exchange point, then the traffic can pass through that, and it can flow within local, right? It doesn't need to really go out to international and come back again to your own network. So these are again, ways we can optimize how we can, or optimize the flow of traffic, right, within certain infrastructure. So Internet Exchange Points is a point where many ISPs, many providers, they connect to one point, what we call an exchange point, so that they can share traffic. They can have transit between them, so that we can achieve optimum results. Response time is pretty good, and we can actually get the best out of in terms of the internet or the routability, right? So this is how the high-level view of global internet then. So we have global internet providers on the top, and then we might have some regional internet providers as well. And there are content providers who provide contents, right? These are all part of that. And then there are providers who provide access, right? Accessibility. And then we have customer networks. We have internet exchange points. So these are all parts of internet infrastructures. We connect from one network to another network and so on. So if we want to, of course, have a proper design, an optimal design, then we connect accordingly, based on those practices what we discussed before, through an exchange point and so on. Okay, so that was some information about internet routing, how it works, how we get information from one place to another place, or how these networks are announced and how they are routed. Now then we get to internet names. Now first of all, why do we have internet names, right? Because usually even when we visit websites, we just type a name, right? There are lots of, we can easily, remember these names. We can easily remember these names, right? We, in a single day, we might be visiting so many websites. We send emails. But actually, why we have names? Because names are easier for us to remember. We are all humans, and for us it's quite easy to remember. But behind all these names, what we really have, we have addresses. Whether we have, we could be having IPv4 addresses, or we could be having IPv6 addresses, anything, right? So, but the bottom line is that we have these addresses behind our names, right? So what happens really then? How these internet addresses versus domain names comes into the picture? So let's say I have my device and I want to access, or I want to visit the website of APNIC, www.apnic.net. So what my device will do, my device will basically send a query to this system called DNS, or DNS system, domain name system, so that simply I'm asking, I want to connect to www.apnic.net. I need the IP address of that web server. So the DNS system then supposed to give me the IP address of that web server. So in turn, my device can then directly talk to that particular web server and establish the connection. So that's the whole purpose of DNS system. But let's see how it really works. DNS system, to work properly, it has to have a proper hierarchical structure. So this is a kind of proper hierarchical structure we have defined. So we have this tree hierarchy called DNS hierarchy. On the top, we have this thing called root DNS. And then underneath that, we have things called top-level domains, TLDs, or top-level domains. These are very familiar to you. Nowadays, we have so many of these, around more than 300 of those, .nets and .coms and .edus and .id, country codes, all these things are there. They're all top-level domains. And underneath that, there are next-level domains, right? So those top-level domains, they can delegate. They can give part of their responsibility to these other domains, right? So they do delegations and so on. So finally, until it reach our web server level, right? Until it reach the web server level, we can do always these delegations, okay? So if, let's say, if we want to visit, now in this case, we have a website, IGF2013, www.igf2013.or.id. So if we want to visit this website, in other words, if we want to visit this web server, how does it really happen? How, where this query is going to go? So I have my device, I have my laptop or the mobile phone, whatever it is, and I want to browse this website, which is www.igf2013.or.id, right? So in this case, when I want to visit this, basically I'm a client, right? I'm a client. So I send a query to a server, right? The client send a query to a server requesting, I want to visit that website. Remember, behind that website, what we really have is an IP address. So, in other words, my client, or I am myself, I'm asking is, give me the IP address of that web server, right? So I send this request to my local DNS, right? So in this network, let's say now we are all connected to this network through wireless, for example. Now, there is a DNS server in this network which will answer for all those clients. So we all, as clients, we send the queries to our DNS server, and DNS server then, if you remember the hierarchy which I showed you before, the tree hierarchy, we have root name servers, we have top-level domain name servers, we have next-level domain servers, and so on, right? Authoritative servers. So our local DNS server will go and talk to these root name servers, right? Send a query to root name servers asking for the IP address of that particular web server, which is www.igf2013.or.id. Right? So root name server stands on the top of this hierarchy. So root name server has got all these delegations. So not necessarily root name server will give me the answer. Instead, root name server will give a reference to the next level. So root name server will say, go and talk to .id name server, right? And it will return the IP address of .id name server. And then .id name server will return the IP address of next level, which is .or.id name server. They are all authoritative name servers which are authorized to give answers for that particular zone, which is, ID or .oid and so on. And then next, the same thing, my local DNS server then will go to the next level and ask a question from the IGF2013.OID name server. And once we ask that name server, it is authorized to give the answer for www, which is the correct web server that we are looking for. So basically what we are trying to do here is that we go through the hierarchy. We go to the top, we go to the next level, we go to the next level, and so on, and we try to find that end result. So this query has to happen all the way when we look for some information. And then once our local DNS server gets this information, it will return the address to the client which asked that question, so that the client can then establish connection with the appropriate web server. So this process happens. So whenever you try to visit a website, right, even when you send an email, things like that, right? So this, when we need to find DNS names or the IP addresses in this DNS system, it needs to go through this process and find the answers. But if this has to happen every time, again the performance factor will be affected. It's not going to be very good. So that is why we have some mechanism here called caching. Means these For example, in this case, the local DNS server is what we call a recursive name server, can keep the answer in its memory or in the cache. So that once, if I'm a recursive name server, once I find an answer after talking to many other servers, I can keep this answer for a certain period of time in my memory, so that when the next client come and ask the same question, I can straight away give the answer rather than talking to many other name servers. Okay? So that's about DNS. Now the next thing is, we also have something called reverse DNS. This is the other way around. Because nowadays, when we do all those, different kind of queries in the internet, we cannot believe every query. Some queries can be bogus, some queries can be fake, and so on. Spoofing is there. So there are, of course, things that we can't always believe. So for example, if someone comes to me and tell, I am so and so, I live in that address, that house. Can I believe it? No. I can't really believe it. Maybe he could be lying to me, right? So if I really want to see whether that person is really living inside that house, maybe I should go to that house and find out whether he's really living there, right? Something like that. So if I'm a secured server, if I'm providing some secured service, I get a query from a certain host saying I am host.isp.net and my IP address is 203 something dot something dot something. Can I believe it? No, I can't believe it, because that could be spoofed. So that is why what I would do is I would look for the IP address what it's claiming to be having and check whether is that IP address really mapping to that particular name. This is what we call reverse DNS. So what we try to do, we try to map an IP address to a name. Right? So this is another process which is actually quite important, especially from operational point of view. When any organization, any operator, when they use some certain IP address blocks, they should make sure that these IP blocks are reversely mapped as well. All right, so we talked about a number of things. We talked about the networks, the protocols, and how we send this data from one place to another place, the internet addresses, IPv4 and IPv6. We talked about routing and how we route from one place to another place, the routing table, the routers, what they do. And then we talked about the domain names as well. And with all these things, what sort of challenges that we are facing today? Now, we are talking about a whole big ecosystem, internet ecosystem here, right? So you can see we have lots of bodies. If you see the outer ring here, the purple one, right, the outer ring, they are called enablers. Right? There are various organizations, various bodies, communities. They make it enable. Right? In other words, for example, governments, regulators, they have to have proper policies. You need actually something like a multi-stakeholder model here so that everyone can work together, right? So you need to have governments, regulators, they work on that aspects, the policies aspects, right? Then we need to have industry associations, NGOs, operators, network operators, right? They all have to get together, standard bodies. Someone has to develop these protocols, because if the protocols are not developed, if the standards are not there, we can't really make it operational. And then name registries. We talked about domain names. So someone needs to actually take care of the domain name side. And then similarly, we have number registries, the IP addresses. Without IP addresses, these things are not going to work, right? So there are various bodies has to come to a common platform and to work so that we make the internet available or enable, right? Then we have to have providers. So when that is the inner ring over there, the blue one, so we have content providers, access providers, applications. Now it's no point everyone else work together, but no one is going to provide content, right? We have to have content, and then we have to have applications. If no one is producing applications, it's not going to work. No point. And then finally, the core is internet users. If we don't have users, nothing is going to work anyway. Right? So we have to have users as well. So it is a system, it is an ecosystem where we have to really work together in a multi-stakeholder model. So we have, we get to the point of internet resource management here. So we talked about various internet resources, like IP addresses, domain names, all those resources. So we need to actually, efficiently use those resources. That is very important. Then there is this important factor called aggregation. I mentioned you earlier about limiting routing table growth. Because if the routers cannot handle the routing tables, it's going to be very hard to manage the internet operationally. That is why, especially the internet operators, ISPs and so on, when they announce these internet address space to the routing tables, they need to take care of that. Otherwise, the internet can be, performance-wise, internet can be, we will face quite a lot of problems in terms of managing that performance. Right? Then we have the registration. Now, registration is also a very important aspect here because these are all public resources. For example, IP addresses, they are all public resources. Now, if we are going to distribute these public resources to various organizations, various networks, various bodies and so on, operators and so on, they need to be properly registered. If they're not properly registered, then only so many things, maybe even nowadays we face a lot of issues. There are a lot of issues and challenges. There are things like spamming. There are things like illegal web hosting, various things, right? So we have challenges to face. There are, hard to handle those. So the thing is that is why the registrations are also very important, because if someone is someone is using these resources in their networks, proper registration will ensure that we can manage those blocks efficiently. Right? So fairness, consistency, these are all important aspects in terms of internet resource registration and internet resource management. So having a secure internet is, of course, the biggest challenge, or one of the, especially nowadays, to make sure that we try to achieve a secure internet. So there are a number of aspects in terms of security. Confidentiality is one important one. We have to make sure, if we want to send some confidential information, so we need to achieve that. Integrity, we have to make sure if we are sending something from one place to another place, if the integrity is lost, if something is changed, if something is tampered in the middle, we should be able to identify that the integrity is lost, right? And the availability, if something goes down, we still should be able to make it available. So all these things are important aspects when we talk about the security of internet. So these are all, the issues and challenges that nowadays we face, where we will have to address those. We have been, if you see the last number of years, we have been evolving. We worked with more of, LAN type of networks, local area networks. Then we sort of, worked more of online sort of content. And now we are moving more of cloud computing and similar sort of lines. So this is where we are evolving. So considering this evolvement, of course, we will see, in fact, to some extent, some of these things are still even nowadays available. We are expecting everything around us will be connected, right? Even in a household, all these devices, what we use, our home appliances, and all these things will be connected, and we should be able to deal with these devices, these things through internet. So this is why actually internet is very important. It's going to be, it's so close to our lives now, and I think all of us are here to actually, to discuss how these things need to be, how we should actually head to the future. So I think with this one, the main thing is that we need to, as I said, we work on a multi-stakeholder model so that we can try to actually understand how this internet works, and then see what are the issues and challenges and so on, and then try to find solutions. So I think with this, my presentation, I end this. So if you have any questions, I can take some questions as well. If not, even we can still discuss around the break times and so on. So I'm happy to answer any questions if you have.
You were talking. Oh, sorry.
Right.
You were talking about IPv4 and IPv6. Is the intention to run both in parallel, or will the IPv4 be converted to IPv6?
Okay, it's a good question actually. Now it's like speaking two different languages, right? So if you speak one language, if another one speaks another language, so we need to have some kind of mechanism so that both parties can understand each other. So if you just say IPv4 and IPv6, if they talk each other, they cannot work together, because if I only understand IPv4 and if I get IPv6 packet, I will drop it because I don't understand it. So we have to then come up with some mechanisms, some technologies where we let those devices understand IPv4 and IPv6 packets, basically, right? So there are a number of technologies nowadays that exist. For example, I can tell one of those, tunneling, which is a very popular mechanism nowadays. So in tunnels, what we do is we try to work on a model where what we call a dual stack model. Dual stack means you understand both. So you have IPv4 stack as well as IPv6 stack. So when those dual stack devices gets an IPv4 packet or IPv6 packet, they can understand both because it understands both. And then depending on that, they can create tunnels between those dual stack devices, so that in between, even though there are IPv4 networks only, they can still send those IPv6 packets by encapsulating. I mean, I'm going into a little bit technical terms here. Encapsulation is basically you are adding a v4 header into your v6 packet so that we can send it through v4 network. So there are technologies like that. So to answer your question, simply if we just try to talk IPv4 to IPv6 hosts, it's not going to work, right? So we need to have some kind of mechanism or technology, transition mechanism, so that we can move from IPv4 to IPv6. Now this issue, or probably this concern, is going to remain for, I think, next few years or so. But maybe after another 10 years, 15 years, when we have lots of IPv6 networks around, then probably you don't need to worry about it, because we have pretty much a bigger IPv6 internet. So even v6 can just talk to, because we have lots of IPv6 networks. But during this transition period now, since we are moving from v4 to IPv6, then we will have to have those any of those transition mechanisms so that we can send those v4, we can talk between v4 and v6. Okay, it's a very important question, especially say that if you run your web server, if you run your website on IPv4 address, right? If your web server has IPv4 address, now in my laptop I have IPv6 address. If I try to access your website, I cannot, because I have IPv6 and your web server is running on IPv4. So that is why it is important that, especially moving forward, we have to think about those aspects. So if you're only running your services, it could be a website, it could be any other service. If you're running only on IPv4, this is something that you might need to think about, because day by day, more and more networks are given IPv6 addresses. So definitely you will need to make sure that you provide your services to IPv6 customers as well. Okay. Any other questions? All right. If there are no questions, I think we will end the session here. And if you have any questions, we can even catch up during the break times. And hopefully, you had some information out of these sessions. And thank you very much for your participation. Thank you.